Hi, everyone. And flying in the middle of the night, he swoops in, and then he lands. He's flying, flying, flying. And then superhero Yankee lands and saves the day. Woo! Q, Q, Q. Yay. So isn't that a fun story, Yankee, right? You swoop in and you save the day with your little cape. And that's a great story now, isn't it? Well, Yankee, there are awesome, really cool stories, and you're always going to be a little baby to me. So let me tell you a story about the Tib-Shirani method. Actually, it's a story about a story, Tib-Shirani method. And I talk about this more, Yankee, but for now, I want to show you how you can use those tools. So, hi everyone, I am Sanya Kuller, and in this video, Yangshi, the superhero guy, and I will be talking about the story Tib-Shirani method for calculating p-values, and in particular, p-values that are adjusted, and those are known as q-values. So q-values are p-values from different experiments that are adjusted, and they are adjusted using the story Tib-Shirani method. So how to use q-values, and in particular, how can we use the q-value package in Bioconductor? That's what we will be talking about in this video. So we're going to talk all about this cool little story, Yankee. It's a nice little bedtime story. You can see in the back that it's just the right time for a little story. And Yankee, I'm telling this to you so you can be a superhero. Swooping. So Yankee, this is a bedtime story like no other. We'll be learning all about the story Tib-Shirani method and how you may apply it. And guys, if you haven't already, please hit the like button, please subscribe. And if at the end of the video you still have questions and you've watched the other videos, please do reach out with any and all questions that you have. So this is Superhero Yankee, and I am Sanya Kuller, and we're looking forward to teaching you about the q-value package in this video. Shall we dive in, Yankee, and talk about this really cute bedtime story, the story Tib-Shirani method, and how we can use it and use the q-value method packages in R? But let's get started. Okay, I'm telling this little superhero a nice bedtime story. So there's this q-value package in R. And what this q-value package is it is enabled to help us calculate the story Tib-Shirani method for false discovery rate control, which I talk about in other videos. So in general, what this package does is we just have to give it a list of p-values that can come from testing many different hypotheses at the same time. And it estimates their q-values and local false discovery rate values. So the q-value of a test measures the proportion of false positives incurred, called the false discovery rate, when that particular test is called significant. So when we have multiple testing that is done, sometimes we can call some p-values as significant when they actually may not be significant. And this happens, Yankee, because as a superhero, many people may cry out to you, save us, save us. You know, it's a boy who cried wolf effect, right? And I don't want you to ever feel like a call isn't important. But sometimes as you're rushing out there to save so many different people calling out to you at the same time, Yankee, and sometimes they may not all be significant calls for help. I don't want you to lose faith. So that's the same idea as a false positive. Conducting many different tests, Yang-Chi, if we do get p-values that we think are significant, we may reject the null hypothesis and say that, okay, this p-value is significant, then this test is significant. And we may be testing tens, hundreds, thousands of different tests. And if we think that many of them are significant, Yang-Chi, if we think that all those calls out there are significant, that no one's pranking you, then what may happen, Yang-Chi, is that maybe you could sadly get pranked. And then I don't want you to lose your faith in these calls, right? We need to be very careful and make sure that we really understand the full story before just swooping in there to help. That's the same idea. And the Q-value is one of those tests that is applied to adjust the p-values that we get. So the local false discovery rate measures the posterior probability the null hypothesis is true given the test's p-value. So given a p-value, what is the probability that the null is true, given what we have observed? Various plots are automatically generated, allowing one to make sensible significance cutoffs. Several mathematical results have recently been shown on the conservative accuracy of the estimated Q values from the software. And this software, Yang-Chi, can be applied to problems in genomics, brain imaging, astrophysics, and data mining. So basically, where there's so many problems out there, Yang-Chi, even astrophysics, like the stars behind us, basically anything where we have a lot of tests taking place. Okay. So let's get started. And in this example, I'm going to have 3,170 different p-values. And I'm just going to show you how we can use the qvalue package for us to do and calculate the adjusted p-values using the story Tibshirani method. And some of this intuition comes from this GitHub site here and qvalue estimation for false discovery rate control. The qvalue package performs false discovery rate estimation from a collection of p-values or from a collection of test statistics with corresponding empirical null statistics. And this package estimates Q values, the proportion of true null hypothesis, which is pi 0. This is pi 0 that is written as, it's an estimate, it's an estimate with a hat. The true one just does not have that. And local false discovery rates, the possibility of saying that there is a significant call out there when it may not be the case, Yang-Chi. That's what it means. When carrying out multiple hypothesis tests, one typically starts either with a set of p-values or test statistics. Either quantity yields a natural ordering of tests from most significant to least significant. For example, if we looked at just p-values, if we rank them from smallest p-value, that would be the most significant because it's the probability of observing what we have observed if the null is true. And if the null is true, there is no significance between the, that p-value is not significant. So the smaller the p-value, the more significant it is, the higher the chances of us rejecting the null hypothesis. So whenever we have a test, there is some natural ordering of the results. When, in our case, we have a bunch of p-values. So let me show that here. We have a bunch of p-values. And all these p-values have some natural ordering to them. So we have 3,170 different p-values, and there is some natural ordering to these p-values. If I were to view these p-values, for instance, I would see that these p-values have some ordering to them. I can sort them from smallest down to largest p-value. And that would take me from least significant down to the most significant p-values. So similarly, We could order them. As another example, if we use F statistics, we could order the test from largest F statistic, most significant, to smallest F statistic, least significant. And it's the same idea where the higher the F statistic, the smaller the p-value would be, for instance. So it's analogous. Either you can use p-values or you can use statistics in this case. We can then ask the questions. Oh, he's already falling off the sleep. Good little guy. Yankee, you may then ask the question, if I draw a significance threshold somewhere along this list, how much can I trust the top of the list? If I say certain things are significant, how likely is it that they are significant? So that's what we'll talk about, how the story-Shivani method can help with that. It's one of the multiple testing correction methods. So another possible question is, where should I draw the line of significance along this list so that we can expect that at most 10% of the list I called significant is composed of false positives, and the others would be probably hopefully true positives. We don't want to be making false discoveries. We may also wish to know the reliability. So this is the package here. We may also wish to know the reliability of a set of tests called significant for all possible thresholds simultaneously. Or we may want to estimate the probability that any given test is a true null hypothesis. So this qvalue package performs various estimates that allow one to answer these questions and other questions. The quantity of interest is a false discovery rate, FDR, which is roughly defined to be the expected proportion of false discoveries, of false positives among all tests that are called significant. So Yankee, you'll be swooping in there, fighting crime, left and right and center. But sometimes when you're getting those calls, how many of those calls for help could actually be false positives and not really significant, right? You really want to help out the people who need help, right? So we really want to control this false discovery rate, this false positive rate. We want to help control it. So we could use things like a qvalue. So let's check out this qvalue here. So an overview of FDR and its well-established methods and theory may be found here. Estimate the q-values for a given set of p-values. The q-value for test measures the proportion of false positives incurred, the false discovery rate when that particular test is called significant. So there's a lot here. But what I want you to see here is the following, that this is this package here, and we can install it. So now it's available on Bioconductor. So if you need to install it, you first need to make sure you have BioC Manager installed. If you do not have that installed, please install it here. And I do have other videos talking about installing Bioconductor and mainly BioC Manager, so you can install Bioconductor packages and also potentially other CRAN packages. And then once you have those installed, please do install, if you do not already have it installed, please install qvalue. That's really key. So that's what we see here. So if you do not already have it installed, then please do install this here. So we're going to do library qvalue to load in the package once you already have it. And we saw the set of p-values here. 3,170 p-values. So I showed the histogram here, but it's really important before we use the qvalue package for us to check a few things about the histogram, Yankee, of p-values. So I'm just going to show 20 bins here. If we want to show more bins, we can do that too. We can even show like, let's even show 50 bins or something. So that's a number of histogram bins that we can show here between 0 and 1. So each will be like O2, so 2% if we have 50 bins here. And it's important for us to check a few assumptions. So right now, let me just move it back to 20 for the sake of the plot. Okay, so it's super important for us to check a few things about this histogram here. To begin with, we must check some things. For instance, according to the package, it's important for us to check that the histogram has a right tail distribution. Something like this, it's really important that we have something like this, skewed to the right. A right tail distribution, Yankee. It's a little smiley. It's really important for us to have a right tail. So the p-value should be relatively flat at the right tail of the histogram. This is an important step in testing whether the null p-values are distributed according to a uniform 0 to 1 distribution. So we should have these p-values start to at least flatten out around here. That's what we really want. It should be kind of like flattening at some point. That's really, really important for using this qvalue package. We should have something like this, because we are assuming a 0 to 1 uniform distribution. The probability of observing p-value in any of these intervals should remain relatively constant, but we should at least, if nothing else, see that it starts to flatten out in this direction. Suppose that we have something like this, and do we observe this in our data? So the first thing we can do is we can plot a histogram. So p-values is a vector. If I were to view the class of p-values, I would see that it is numeric. If I look at the structure of it, I would see it's a numeric vector of 3,170 p-values here, Yankee. That's what I would observe here. And when I plot the histogram, I would see that it looks like it's starting to flatten, like, maybe it's going up a bit, but it looks okay for now. It's maybe problematic a bit, but it still looks something like this. So what's really key here is that, we look at this data and we make some sort of assumptions where, okay, it looks like it's kind of maybe flattening out a bit. That's what we want to see there. What would be really problematic would be to see something like this, where it's a U-shaped distribution. If we notice it's like a U, then that's a problem, where it's like going all the way down and then coming all the way up. That would be a problem, where it's going all the way down and then coming up. That would be a U-shaped distribution, which would be bad. So we just need to check and make sure that this assumption is met, where it's not a U-shaped distribution. Instead, it should be something where it's like coming and staying relatively flat. Even if it kind of goes up a bit, it should not be peaking back up. So this U-shaped p-value histogram would be a red flag. An important assumption behind the estimation performed in this package is that null p-values follow a uniform 0-1 distribution, which would result in a p-value histogram where the right tail is fairly flat, as in the original Haden-Fock p-values, which I do talk about in other videos where I talk about the breast cancer BRCA1 versus BRCA2 dataset. So if we have something like this, which is problematic, it could maybe indicate that we used a one-sided test on data with a signal in both directions, or maybe there's a dependence among variables in the data. And in that case, we can use the SVA bioconductor package. So in either case, it's usually possible to compute the p-values using a different model or method that will yield p-values that better match the underlying assumptions of the methods implemented in this package. So we're going to look here at this qvalue function, Yankee, and we're going to try to calculate these q-values now for our set of p-values. So let's say that for our assumptions, it looks okay. So then what we can do is just call on this q-value package here. Okay. So all we need to do really is just to plug in Q values. Okay. So the simplest thing that we need to do would be just the following. We have our set of p-values, and we just, like, that's what this could be for if we use the Haddon Falk data, whatever it is, that is a set of p-values, and we just plug them into this package Q value, and this will give us a Q object. And the Q object will have quite a few things, but several arguments can be used in the function Q value. And the main input that we really need is just a vector of p-values. This is the only necessary input. How can you calculate Q values if we do not even have the p-values? So we only need this, but the other things are things that can help us. Okay. We can also have false discovery rate level at which to control the false discovery rate. So typically, we can use alpha is 5%. So if this is selected, a vector of true and false is returned in the FDR level slot that specifies whether each Q value is less than FDR level or not. And then an indicator of whether it is desired to make the estimate more robust for small p-values. This uses the point of positive false discovery rate. It's optional. We can also use additional arguments like lambda, which is passed to the pi zero estimate. We can also use pi zero method. By default, lambda is tested for every 5% increments from 0, 5%, 10%, 15, all the way to 95%. And just to clarify what this is, by default, we are testing this set of lambda values. So if you want to change any of those, then we have to check what those are. So lambda is just a sequence from 0 to 0.05 that at 0.95 that is going in 5% increments. So 0, 5%, 10, 15, 20, 25, 30, 35, 40, 45, 50, all the way to 95%. That's what lambda can be, any of these values which we do test in the end. So if you have a vector of values, you can use those values as testing. Pi zero method is passed to the pi zero estimate. And what that's doing is it's going to be smoother or bootstrap. The method for automatically handling the tuning parameter and estimating pi zero. And there are some additional things. So in our case, let's just try this out, Yagchi. Let's just see what we will get from these assumptions here. So let us just try these out and see. Okay, so all I'll do is I'm going to take my p-values here, all these 3,170, and I can just pass them into this Q value function right here. You can see FDR.level is none, PFDR is false, LFDR.out is true, pi zero is null. Everything else is set as the defaults. So I'm just going to run this. And I'm going to see that I have a Q object. By default, the lambdas would check from 0 to 0.95. And associated with each lambda, each of these lambdas, is the pi zero lambda, which is the estimated proportion of null p-values for a given lambda. So a given lambda represents a given spot where we start to think that the histogram is leveling out. That's what it represents. So if we're going all the way from here, like we could even say, okay, well, let us suppose that it's starting to maybe flatten at 0.58, for instance. So if we say, okay, well, let lambda, then what we're really doing is we're really trying to see for a given lambda that we're estimating, what is the estimated proportion of null p-values that we get. Another example could be like if we are saying, just to choose something that is shown, we could have even side. Okay, well, let us suppose that it's starting to flatten around 0.4. Or 0.45 would also be nice too. You could choose 0.45. We could choose lambda is 0.45 Yankee. So we're thinking at this point, maybe it starts flattening out. So what we're going to see is the ninth one. 2, 3, 4, 5, 6, 7, 8, 9. To be 1, 6, 7, 8, 9. This is the one. So the estimated proportion of null p-values would be 0.6859765. And we could also check if we use some smoothing, that this is what it would look like. It would be this value here if we use some smoothing on these p-values, estimated proportion of null p-values, because we don't know how many are actually null. So the key idea is that we are getting this Q object here. This Q object comes with quite a few things that we can see by looking at str Q value. You can see it's a function. It has all of these things here. It's a class of Q values. They have the LFPR. They have the p-values. These are the original p-values that we had passed in. And they have, most importantly, the Q values. They also have the pi zero that they went ahead with. We could have specified a given lambda, but if we do not, it's just going to go with the default set of lambda values, and it's going to try those out. So if we want to get the pi at the lambdas, we can do this. These are the lambdas that were ultimately tested. These are the lambdas that were tested. These are the associated estimated proportion of null p-values. It's almost like a list. To access each of them, we just have to put this $sign and what we're looking for here. This is the pi zero lambda. If I still want the p-values again, I can also just say p-vals, and it should be the same thing. In fact, I can even expand this. I can see that we have p-values, q-values, LFDR, pi zero lambda, lambda, and pi smooth. These are the arguments we have here. Now, these are the Q values that we've actually wanted. So we just have to call Q values. So we have lambda. We have estimated proportion of null P values here. We have our P values, which is the same as original. And we have our Q values here. And we could also just do a data.frame. So this data.frame would show that we have the P values here and we have the Q values here. So the multiple testing correction basically helped us go from the P values to the Q values. That's what it is, Yankee. Yes, at the end of the day, we have these original P values and we have gone to these Q values here. That's the key thing. That's what we get from this multiple testing correction. We get a set, Yankee, of these corresponding Q values for our set of P values. We have this set of Q values here. I can just call it like result. And I can also just do call names. So we can see the P values and the Q values. So each P value and each Q value, so the smaller the P value, the smaller the Q value will be as well, typically. So we expect that this relationship actually will be preserved by the Q value. So we can sort by the P value, And we can see how the Q value tends to relate to that as well. When the P value is 0, the Q value is 0 as well. And then we can also see that when the P value is at its highest, like 1, the corresponding Q value will be 0.7238, which if we look at it here, if I look at Q object pi 0, this value here, which is very, very interesting, this value right here happens to be the pi 0 overall. The maximum Q value that we get in our data set will be the same thing as the Q object pi 0 estimate in the end. The estimated proportion of null P values that we go with will be the same as the maximum Q value in the end. That's actually really, really interesting, Yangshi. That gives you kind of a few goosebumps, hopefully. This is the same as this. They're the same. And this, again, is the pi 0 that we're going with. Pi 0 estimate. So this hopefully shows you how we can just go for our given set of P values to our Q values. We could call this. So all we did was call this over here. We can see the summary of this as well. We can see, we can call the summary and see the pi 0 were estimated in cumulative number of significant calls. You know, for P values less than this. So we can see how we compare for these P values here. How many P values are less than 1? Well, 3,169. There was one P value in our list. If you recall, there's one P value that is actually 1. You see, it's 1. So that's why this is 3,169. But if we look at the Q value, then there would be, all of them will be less than 1 because the maximum Q value is actually the same thing as this. They're the same. And that's really interesting. They're the same. So if we look at how many P values are less than 0.1, looking at the P value and Q value, how many are less than 0.05, what we should see is that for the P value, this number here, for each corresponding set of possibilities, the P value right here. So I just want you to see these metrics. If you look at the summary, this will give you metrics of local false discovery rate, Q value and P value here. And you can just see that, for instance, we have 2 Q values that are less than 1 times 10 to the negative 4. We have even more P values, you know, that are less than this. More P values are less than this. In general, the P values tend to be smaller than Q values because we're doing this adjustment. So we're tending to raise up some of these, you know, we're tending to raise up some of the Q values in general. We could even look at this histogram here. And this will give us the p-value density histogram that we were looking at before, but now this is density instead of counts. And we can look at the false discovery rate and the Q values here. And ultimately, we can see the estimated proportion of null p-values, which is 0.7238. That's what this will be over here. This is our estimate that we were trying to find. This right here is the estimate. This is our pi 0 hat that we were trying to find from our lambdas. That's what we can find over here. We can see how this relates here. And we can see that ultimately, this is the best one that we found at this point. You know, the p-values start to flatten across. So that's what's key over here.
We can even plot this Q object here.
And if we plot it, then we can see how for given values of lambda, we can see different estimated proportion of null p-values here, which we did see. If we look at the lambda, we look at the pi 0 lambda, and then this in red is the smooth one. We have smooth, pi 0 smooth. This smooth is the same. East. It's kind of like the same. And then the pi 0 lambda is this right here, each of the black points. And each of our lambdas that we were looking at, every 5% that we were looking at, 5% up to 95%. These are the lambdas. These are the estimated proportion of null p-values. That is the y-axis here. So that's what this is over here. That's what we're looking at, estimated proportion of null p-values for given sets of lambda. It's a function of the lambda. And we can see that ultimately we are going with 0.724. So our Q values, significant tests, expected false positives here. And ultimately, if we want to, let's say, go with lambda being like 0.7, or if we want to go with lambda being 0.58, we can rerun this analysis. And instead of testing many different lambda values, we're just going to be testing one lambda of 0.58. We're going to get a pi 0 for this lambda. We're going to then get different metrics. Like this pi 0 will be different. Q values will be different for the same set of p values. Local false discovery rate will differ. The pi 0 lambda will change if we specify that we want lambda now to be 0.58. We can then see the summary of this will be different as well. We could also look at the histogram of this Q object now again. And we can see how this will now be 0.671 here. We could also look at plotting this Q object with just this one lambda. And we're going to just see that we have considered just this one lambda. We do not look at anything else. So I just wanted you to see that there are multiple things. Like if you have the own set of lambda that you believe in, you've looked at this, if you have your own set of lambda that you believe in, where you start to think that this starts to peter out or starts flattening, then you can also input your own lambda in here and have it run estimates for that. Instead, you're going to see that we just have lambda, pi 0 lambda, and pi 0 smooth. There's no smoothing to be done because we're not testing multiple lambdas out. We're just choosing one. So smoothing really just comes from having a bunch of lambdas. Like if we go back to what we had before, where we have multiple lambdas, we applied smoothing so that we can fit a curve. Like here, it's like a parabolic curve. We try to fit through these lambdas, try to be a good estimate for what's going on. That was the smoothing, just like a line of best fit. Here it's like a curve of best fit, so to speak. But I just wanted to share with you those insights on the Story-Tib-Shirani method and on the key value package. And there are a lot more things you can do, but I just wanted to help you get started with calculating the Q values for a set of P values. If you have a set of P values from any tests, this will help you calculate the corresponding Q values from them. Ultimately, in the end, we are going to go from our set of P values. Yeah, he's already falling off to sleep. We go from a set of P values all the way to the corresponding Q values. So these are the testing correction that we want for multiple Q values. So I hope that this was helpful. I do have other videos on adjusting P values and multiple testing correction. So I hope you found this helpful. If you did, please do reach out. If there are any and all questions, please like, please subscribe, and stay tuned for this local little hero coming to rescue you. I am Sadia Koller, and this is cute little Yankee. He's a little superhero. And he's swooping in to save the day, and he's telling you, please subscribe for more updates. Aww. Here's his little cape. Swooping in to enjoy the day. Thank you guys and have a great day. Q values.